Today we're going over impedance matching and how is it used, what is it, and how you can incorporate this into your own designs. So beginning, what is it? So in the design of RF circuitry, impedance matching is often necessary to provide the maximum possible transfer of power between a source and its load. What this means is you're trying to move something from A to B. You want the maximum amount of power to be shifted. You do not want anything in between that, something that could reflect it or block it in that kind of source, in that kind of way. This is what impedance matching is to provide us with, is to let us transfer stuff from A to B. So it is said in DC that the maximum power transfer will be transferred from a source to its load if the load resistance equals the source resistance. Though in AC, the same is said in this same theorem, that the maximum transfer power from a source to its load occurs when the load impedance is equal to the complex conjugate of the source impedance. What is this complex conjugate? Sounds like a spell or something. It simply refers to the complex impedance having the same real part with opposite reactance. An example of this would be if the source impedance was ZS equals R plus JS as on screen, however you'd say it, and then its complex conjugate would be ZS equals R minus JX. And you can just see it's just only been a change of a plus and a minus. And what you're trying to actually get it to do is to make it so it sees one another. So you want to make sure the source sees it as this load, and you're trying to equal it out essentially to get that maximum power transfer through. Hence why there's a plus and minus. Of course, I'm very much oversimplifying it. There's a lot more. I'll put in the link description to a talk to someone who explains it much more better than me. But here I'm trying to get you up and running with something. So where is it being used? So this is a snippet from a piece of circuitry I've done, and you've probably seen it in this pi filter configuration. And this is what is meant for. So this would be on a RF line of some sort, maybe leading from a microcontroller to antenna. This is the most cases I design with, and usually you see it in this configuration because it needs it so the antenna can be matched towards a micro or the micro matched towards the antenna, whatever it is. There's different types. You'll see it all. It comes in different flavors. And this is what I mean. So commonly you see it as a 3-element pi network. From what I've seen, of course, there's also the T network. You also see them in an L network. So you see them as a standard low pass filter or high pass filter. Whatever it is, you see them in all different shapes and sizes. And there's methods to how to calculate them, how to do them, how to get the values with your Smith chart mathematically, whatever your weapon of choice is. And that all depends on you really, but this will not be covered in this video. Quite a lot of the time the datasheet is your best friend, and you can find a lot of information regarding how to hook up these things, what you need to do. So here we have an antenna in front of me, SR4G008. It's by Antonova. I don't know if you pronounce that. And what we're going to go through here is look at all these things, and I highly recommend you read it if you know what you're looking for. But let's say we just want something to hit up. So we go down to its schematic symbol. We know that. Transmission lines. So these are some other things that I'm going to speak about on what you should keep in mind of. And here we are, the matching circuit. So antenna requires a matching circuit that must be optimized for each product, and it gives you recommended. You can even ask them for technical support. This has been really good, especially. But you notice it hasn't given us a value, so now we're still stuck on, how do we calculate this? How do we know what to do? And we can calculate this. We can go through the whole procedure of finding this antenna, what it actually requires to, and we can play around with the values and such. But what if we had a prototype and we wanted something, we really need something quick and easy with a microcontroller? And so what does this mean? Can we just implement random values to give it and call it? No, we cannot really. So what we need to do actually is look for something else, maybe something in our microcontroller schematic that might have it. Here we are in application note 5165, something that has helped me immensely when it came to this type of thing. I believe I spoke about this application note. It is literally a godsend. RF basics, reference board schematics, how to choose components, PCB stack up and technology. It's got it all in here. But if we head over to reference board schematics, it is this portion that we're interested in. And yes, I do believe that totally correct for us per the last video there, where you may not get the maximum that you want. You may not get the most ideal value. You may not even get the maximum amount of power transfer or whatever it is. But this is something that will get you up and running. So for example, if we were using this chip here in this package, the reference, so the nuclear has been optimized for this. But so how do we know it's been optimized for our board? Well, that's the thing. You don't. It's purely independent of what your stack up is and what you've also got going on. Everyone's unique in their own way, of course. And I'm not saying this is completely useless now that I've said it's, you can't do it. You can still use this and you may get it, it's a good chance you're going to get it to work. I'm telling you now that I've used this a lot in my own pieces of work, and I've asked various other engineers who've done this for many more years than I have, and I do recommend to use the reference schematic to get something up and running. I work in an area where we try and take these ideas and we try to put them into a prototype as fast as we can, and to make it, to get a functional thing from a client's idea, And if that's all you're really doing, if you really want to get something up and running efficiently, if you just want to do something at home, the reference schematic is not a bad idea. It really isn't. It really isn't. I do this a lot, as I've said before, and I'll speak about that soon, but you can take these ones if you would. And I'm saying this for all other components and whatnot. You can take these as a good starting ground. There's nothing wrong with that. Again, I've asked many others on what they think about taking reference schematics, and especially with RF, as it's a totally different world and whatnot. And what I've been doing and what others have been doing have said they use the reference schematic to get them up and running. And that's until like certain values need to be tweaked. That's until they're looking for something specific. But if it's something to get up and running, the reference schematic is the way to go. And so you don't have all this headache. But say you wanted to suddenly find out these components, how you would actually do it. How you would actually do it is you using a Smith chart. So you can actually use this to determine the matching network. So you might be finding a value of this, and you would need to use the Smith chart to find a nominalized matching network. So it's asking for a nominalized impedance of 50 ohms. So usually antenna you have is 50 ohms, and you want to try and match it towards that. So both your microcontroller and antenna see 50 ohms. And so this document covers a very base level of how you'd use a Smith chart to calculate these values. I highly recommend it reading. Of course, I want to plug in a very helpful YouTube video that I found and I've used to learn this. So I do recommend you watch that. Now, if we go to this antenna datasheet over here, I'm not going to bother saying this, but this is an antenna I used for quite recently for a Bluetooth project. So within this Bluetooth project, I wasn't even given any values. And this is one thing I want to speak about, is the antenna keep out clearance for your circuit to work, or for your antenna to work, I should say. Usually there's a certain clearance and measurements that you need to adhere to get the maximum, out of your antenna. And it showed this matching network here. I wasn't given any values, and I'm like, okay, so what do I do here? Well, I know something else that has a schematic of some sort that I can use to reference to, and that's the microcontroller that I was using. So here we are in this microcontroller reference schematic from an NRF 52840, and it was this exact piece of circuitry here that I used for that Bluetooth antenna. So you can see here it's got a pipe filter and an inductor, or whatever you want to say, two separate. And this was the exact circuitry. In fact, I used all this circuitry, this whole entire thing here. I just simply copied and pasted because they gave it, and I know it'll work, and lo and behold, it did work in the end, because I just attached the antenna in front, and I copied the antenna layout guide and what did the manufacturer specify, and so on and so forth. Now, for these type of things, it's not only just the antenna that you need to keep worrying about and your impedance matching. There's a lot of things that you need to keep in mind. I've made a separate video on RF design guidelines, but to overall encompass it, you need to have a 50 ohm track as we are working within that, and I've always routed a 50 ohm track unless otherwise for RF stuff. You need to be quite aware of where your ground planes are, where your ground ports are. You need to be aware of where other signals are traveling. Do you have something going under? Do you have a critical path next to it? Do you have a critical component next to it? It's these things to keep aware of, and I'll plug that video in the description. But it's not only just impedance matching they need to worry about to get your things to work.